We present simulated annealing in early layers leads to better generalization. Instead of just doing gradient descent for training a neural network, we propose a very simplified version of simulated annealing on only the early layers of the network. Here's a summary of our method. During training, the later layers of the network always do gradient descent. However, the early layers of the network periodically go through a short stint of gradient ascent and perform gradient descent for the rest of that period. For instance, considering a period of 160 epochs, we perform gradient ascent for 40 epochs and gradient descent for the rest of the 120 epochs. We observe that our method is able to avoid overfitting, surpassing normal training by a large margin. Furthermore, our method has a stronger transfer learning than normal training. Here are the results for transfer learning from tiny ImageNet to flowers dataset. Imagine that we are stuck with the same amount of data for a long period of time. The challenge that arises is the model fits the data well after X epochs, but how to train it for, let's say, 10X epochs? As you can imagine, normal training in this scenario may lead to overfitting. For instance, a ResNet-50 model trained on tiny ImageNet fits the data relatively well after 160 epochs, but when trained beyond that, it faces overfitting and its performance drops. So the overall goal of iterative training methods is to make the best use of the data we already have, given more than enough time, and essentially fight overfit. Here's how iterative training methods work. Periodically, every epochs, when the model has fit the data well and further training is prone to overfitting, forget some useless information to make room for more training. And each period of epochs is called a generation. And forgetting here means any operation that lowers the training accuracy. So at the beginning of every generation, we have a forgetting stage, and the rest of the generation is normal training so that the model recovers and hopefully finds a better minima. This forgetting and relearning analogy of iterative training methods was proposed by Zhu et al. Here we discuss the motivation of our paper. One of the main motivations of our method is to have a better prediction depth. For a single sample, prediction depth refers to the layer after which all layers correctly classify that sample under KNN probe. Now, why is this important? A better prediction depth has shown to have a bunch of good attributes. For example, a better prediction depth leads to better uncertainty, better confidence and accuracy, and faster speed of learning for that data point, which are all desirable. Later layer forgetting is a state-of-the-art iterative training method that aims at improving the prediction depth. In this work, at the beginning of every generation, they randomly reinitialize the later layers of the network and normally train the whole network for the rest of that generation. We saw that normal training suffers from overfitting when trained for too many epochs, but with LLF, the accuracy increases by like 2.5%, and there is no sign of overfitting. However, we raise the question, how does LLF work in transfer learning? Here, we study LLF in a transfer learning scenario. The results show a ResNet-50 model pre-trained on tiny ImageNet and transferred to a few target datasets. We observed that even though LLF has a stronger in-distribution accuracy, it has much worse transfer performance compared to normal training. So the motivation of our paper is to train a network that has both a good prediction depth and is stronger at transfer learning. And the solution we came up with is simulated annealing in early layers. Simulated annealing in optimization has been used for a long time. Let us say we have a landscape that we want to find the minimum of it. Normally, we would do gradient descent constantly, but in simulated annealing, we randomly perform gradient ascent with some probability p, where p is high in the beginning and diminishes at the end. For example, if we are in this curvature, If we do only gradient descent, then we will end up stuck in a local minima. However, if we are somewhere here and we do gradient ascent, then we have a chance to escape this local minima and find a better and global minimum. In this work, we performed gradient ascent on the early layers of the network for k epochs at the beginning of every generation, and meanwhile gradient descent on the later layers of the network. Then, for the rest of the training, we do gradient descent on the whole network. So the later layers of the network are always doing gradient descent, and the early layers of the network alternate between gradient ascent and descent, which resembles simulated annealing. Now, the experimental results. Here, we show that SEAL has a much better prediction depth. As you can see, all layers of SEAL has much better KNN probe accuracy than normal training and LLF. Furthermore, we observed that SEAL has a stronger in-distribution performance than both LLF and normal training. We saw that even though LLF had better in-distribution accuracy, it had worse transfer learning. Here, we observe that our method has a stronger transfer generalization than both LLF and normal training. We extend our transfer learning results to few-shot transfer learning. We observe that the same trend as in transfer learning, that is, LLF heavily underperforms, whereas our method dominates. Thank you for watching this video and your interest in our paper.